Okay, today we're going to pick up where we left off looking at shifts of graphs. The first one that we have here is the absolute value function. We have the absolute value of x minus 3 plus 2. So first, if we describe this transformation, if we look at what's outside of the square, or outside of the absolute values, that's the plus 2, which means this graph is going to be shifted up 2. And then if we look inside the absolute values, that's where x minus 3 is. If it's a positive number, it shifts left. If it's a negative number, it shifts right. So this is minus 3, which means that it's going to move to the right 3 units. Additionally, whenever I think about this, my absolute value of x function should be a v. And so now I'm going to shift to the right 3 and up 2. So my origin, which would have been at 0, 0, is now going to be over at 3 and up 2. Having some serious lag in my writing device. Okay. So now that we have this in place, moving right 3 and up 2, that's going to be my origin point. And from there I go up 1, right 1, continuously, and up 1, left 1, continuously. I can draw a line between all my points, throw an arrow on the end, and same thing with this side, and I'm done. So my plus 2 shifts it up. It's inside the absolute values, it shifts it left and right. Remember, the negative goes right, positive goes left. This was a minus 2 outside here, would shift the whole graph down. Scaling and reflecting the graph of a function. For c greater than 1, it stretches the graph vertically by a factor of c. If it's y equals c times f of x. So if I have a constant or a number times the entire function, then it's going to stretch it vertically by a factor of c. If it's 1 over c, it compresses the graph vertically. Then if the c is just everywhere that there's an x, it compresses the graph horizontally, or if the c is inside parentheses, if we're looking at an absolute value, if it's inside the absolute values, then it's going to compress it horizontally if it's the whole number, and if we're dividing by c, it is going to stretch the graph horizontally. So these work opposite of each other as we look across what it does each time. So in this case, if I start with y equals the square root of x and 3 square roots of x, and I graph that, then first I'm just going to describe what's going to happen to it. Because this is a 3 out in front, it's going to be a vertical stretch. So vertical stretch by a factor of 3. And that's because it's outside of the square root, and it's a whole number. If this had been 1/3, it would be a vertical compression by a factor. Okay, if we just graph these now, if I do the square root sqrt of x, see what that looks like, and then 3 sqrt x, you can see what that one looks like. If we go to a point here at x equals 1, On the red one, it's 1, 1. If I go to the blue one, it's going to be 1, 3. Because it's 3 times, or stretching it vertically by a factor of 3. If I go out to 5, this is 2.236. So if I take 2.236 and multiply it, it's going to put me at 6.708. So this is a vertical stretch by a factor of 3. You can see it on the graph itself. Okay, part A of this one, this is all out of order here. It says, given the function f of x equals x to the fourth minus 4x to the third plus 10, find formulas to compress a graph horizontally by a factor of 2, followed by a reflection across the y-axis. Part B says compress the graph vertically by a factor of 2, followed by a reflection across the x-axis. So if I'm doing it across the y-axis, that's going to mean that I put a negative out in front of the whole thing. But we're doing that after we compress the graph horizontally by a factor of 2. If I think about a horizontal compression, that means it's going to be a whole number, and it's going to be f of 2x, which means everywhere I see an x, I'm going to put a 2x. So that makes this 2x to the fourth minus 4 times 2x to the third plus 10. Two x to the fourth then becomes 16x to the fourth, and it's minus 2 to the third is 8, so it will be then times 4, which will be 32x to the third plus 10. Now I have to reflect it across the y-axis, so that would be putting a negative in front of the whole thing, which means we're going to do a negative out in front here. So I switch all my signs. Negative 16x to the fourth minus 32x to, plus 32x to the third, switches that sign, and then minus 10. For part B, compress the graph vertically by a factor of 2, followed by a reflection across the x-axis. Since I'm compressing vertically, that means it's going to be 1/2 times f of x. So I'm multiplying each of these terms by 1/2. Distribute my 1/2 to each. That's 1/2 x to the fourth minus 2x to the third plus 5. Then it says a reflection across the x-axis, which means I'm going to make my x negative. So 1/2 f of negative x, which means everywhere I see an x, I make it a negative x. So it's 1/2 times negative x to the fourth minus 2 times negative x to the third plus 5. Negative x to the fourth becomes a positive x. I can get rid of my parentheses, just make that x to the fourth. Then negative x to the third keeps it negative, so negative x times negative 2, that becomes a positive 2x to the third, and then plus 5. And that's it for that one. That moves us on to ellipses. The standard equation for a circle centered at the origin is x squared plus y squared equals r squared. We did this examples of circles already. I think it was in the last section or the section before. Okay, whenever we're creating ellipses, we're actually substituting c of x in, where c is just some constant, for x in the equation. So that means that it's going to square this c, because if I'm putting c of x in for x, that would give me c x squared. So we would square both of those, the c and the x. So if 0 is less than c is less than 1, so if c is between 0 and 1, then the equation will horizontally stretch the circle. If c is greater than 1, it will horizontally compress the circle. So if I have my original circle, x squared plus y squared equals r squared, gives me this circle. And if I'm doing c squared times x squared, then that's going to give me an ellipse where it stretches it horizontally, as long as c is between 0 and 1. If c is greater than 1, then it's going to stretch it, or compress it horizontally. So the top is staying the same, your y, and that was the same thing here. Your y stayed the same. It's still r, or your radius of the circle. And what's changing is our horizontal factors. You'll notice they're both r over c, but if this was like 2 divided by 1/2, that would make this -4 and +4. Here, if it's a number greater than 1, so if it's 2 for our radius, 2 divided by 2 would be 1, so it pulls it in horizontal. Notice the y-intercepts are always r, or the radius in this case. Then in the second figure, the line connecting negative r over c to 0, negative r over c 0, and r over c 0 is called the major axis. And the line connecting 0, negative r, and 0, r is the minor axis. Look at the second figure. This is the major axis, and this is the minor axis. And you can tell that because it's smaller. Major is the larger one, minor is the smaller. If we look at the third figure, it's going to be the opposite. This is the major axis because it's the larger. This is the minor because it's the smaller. So our major and minor axes really depend on whether or not we have a horizontal or a horizontal compression or a horizontal stretch. If we divide both sides of the equation by r squared, then we get x squared over a squared plus y squared over b squared equals 1. And in this case, a equals r over c, and b equals r. If the number we get for a is greater than b, then the major axis is the horizontal. If the number we get for a is less than b, then the major axis is vertical. The center of this ellipse would be the origin, because we haven't changed, added or subtracted anything from our x's and y's on top. So what if we wanted this equation of an ellipse not centered at the origin? So we originally had x squared over a squared plus y squared over b squared equals 1. If we wanted an equation centered at the point hk, we would treat it just like the center of a circle. So we would then do x minus h squared over a squared plus y minus k squared over b squared. It would all still be equal to 1. That would change where our ellipse is centered.